We've seen Datalog, but now it's time to see the big thing, and that's Prolog. This time the learning goals are that you should understand the syntax of Prolog, of course, and also how it extends that of Datalog. And to understand the difference between the semantics of Prolog and the semantics of Datalog, because even though Datalog is a sublanguage of Prolog, the semantics is different. There's things you can do in Datalog that you couldn't do in Prolog, and things you can do in Prolog that you couldn't do in Datalog. Another learning goal that's really important is that you should be able to use the programming paradigm for modeling programming problems. So you should be able to model programming problems in Prolog. We have lists in Prolog, just as we had lists in Haskell. So you should be able to write list predicates in Prolog and be able to relate them to how you would write list functions in Haskell. And finally, because the semantics of Prolog is different from that of Datalog, you should understand how that works. And the semantics of Prolog is one of proof search. So that's also a learning goal. So what's so special about Prolog, apart from the fact that there's a coffee bar named after it in Copenhagen? Well, Prolog is the richest of the programming languages we've seen. We've seen Datalog, which is a proper superset of relational algebra, also known as SQL. You can add negation to Datalog, and yet you get a more expressive language out of that. But you can add more features, and then you get Prolog, and Prolog is Turing complete, unlike these smaller languages. So the first thing to notice is that, as we've seen, Datalog is a sublanguage of Prolog, but Datalog corresponds to polynomial time computability only. Prolog is Turing complete, and because some problems are not polynomial time computable, then we know that there must be something more out there. And that's the algorithmic power of Prolog. One more thing, we know that Datalog queries always terminate. But we know that if we want to go for Turing completeness, we must be able to express algorithms that do not always terminate, because Turing machines do not always hold. And in fact, while Datalog queries always terminate, Prolog queries do not always terminate. Of course, that's a source of frustration sometimes, but that's what you pay for having full Turing power. What's the abstract syntax of Prolog? Well, here are the formation rules. A Prolog program is a sequence of clauses, and each clause is a Horn clause with a head and a sequence of atoms in the body. A0, A1 up to AN are atoms. So far everything looks just like Datalog, but there are differences. An important difference is that the atoms, well, they can be predicate symbols applied to sequences of terms. You saw that in Datalog as well. You have negations of atoms. That's Datalog with negation, but it's not just Datalog. Something more is going on here. Terms can be constants or variables, just as in Datalog. But in Prolog, we also allow function symbols. And f ranges over a finite set of function symbols. And that's interesting. One more difference between Prolog and Datalog is that facts, and facts, remember, facts are clauses with no body, can contain variables. But the really big difference is the syntax for terms. We have a term language that allows us to express interesting things. Another difference is that the order of the clauses actually matters in Prolog. That's not the case in Datalog. You can write your clauses in any old order you want, but in Prolog it matters, and that's because the semantics of Prolog is that of goal-directed search. Let's have a look at a program that's got one behavior in Datalog and another in Prolog. And here's the example, the tiniest of programs. What would Datalog tell us? What would Prolog tell us? Let's have a look. One way of seeing the difference between Datalog and Prolog is by looking at a small example that behaves differently in Datalog and Prolog. Here it comes. It's our favorite graph example, a graph with 3 edges, an edge from A to B, an edge from B to C, and an edge from C to D, and a path predicate that tells us if there's a path between 2 vertices. The first clause says that there's a path between x and z if there's a path between some x and some y, and a path between y and z. The second clause says that there's a path between x and y if there's a path, there's an edge between x and y. Let's try to give this to Datalog and find out if there's a path from A to D, and there should be. And oh yes, Datalog is happy. Now let's try to give that same program to Prolog. Let's open the SWI Prolog interpreter. SWI Prolog was happy with that. Let's find out what Prolog thinks. Is there a path from A to D? And we don't write a question mark, we write a full stop here. Is Prolog happy? Not quite. Stack Overflow. Something's gone wrong. There is a difference between the semantics of Prolog and the semantics of Datalog here. And that's because Prolog uses proof search, whereas Datalog computes the minimal model. And when proof search is used, recursion rears its ugly head, but we'll get back to that. For now, we could try rearranging the clauses in our Prolog program a little bit. We could put this one after this one, give this to Prolog, and find out if there's a path from A to D. And now Prolog is happy. So it seems that the order of clauses matters in Prolog, and indeed that's the case. So what this tiny example hinted at was that the semantics of Prolog is different. Every Datalog program has a minimal model that consists of only finitely many facts, and the Datalog interpreter computes that minimal model. Prolog programs have models too, but they can be infinite. And because Prolog programs can have infinite models, the fixed point semantics for Prolog is not very useful, because computing the infinite model would take an infinite amount of time. A better way of thinking of Prolog is by means of the proof theoretic semantics. And we think of the execution of a Prolog query as a proof search. You could do that in Datalog, but certainly we can also do that for Prolog queries. And it's precisely because we think of queries as something that involves a goal-directed proof search that it matters in which order the clauses appear in your program, because the order of the clauses tells us in what order we should search for a goal. Now in Prolog we can use function symbols to build composite terms, and that means that function symbols can also appear anywhere in a clause. They can appear in the head of a clause, and they can appear at interesting places in facts. Here's a tiny program about kings and queens in Europe. First is the fact that Queen Margrethe is the monarch of Denmark, that Queen Elizabeth is a monarch of United Kingdom, King Carl Gustaf is monarch of Sweden, and King Willem Alexander is the monarch of the Netherlands. And we can distinguish between kingdoms and queendoms. X is a queendom if it's the case that monarch Queen Q of X. In other words, that Q is a queen and the monarch of X. Let's try to give that program to Prolog. Now let's feed this tiny program to Prolog, and that's SWI Prolog for you. Here it is. And we can make all sorts of interesting queries. For instance, we could ask which countries are queendoms. We write queendom C full stop, and we get that Denmark is a queendom. By writing semicolon, we get another instantiation of C. That was the United Kingdom. This looks like something we could do in Datalog, but we can do more because we have got composite terms now. We could ask who is the Queen of Denmark? Oh, that's Margrethe. That's interesting. That's the sort of query you couldn't do in Datalog.